So today we start discussing the second part of this last chapter, chapter 10. Well, this chapter is essentially divided into parts. The first couple of sections which deal with parametric equations, in which we did first the algebra, then the calculus on the first two sections. And the remaining two sections, those deal with polar coordinates and a little bit of the algebra and trigonometry, more like, yeah, algebra and trigonometry, a little bit of both. And in the very last section, we'll discuss the calculus in the polar system. Well, so you may have seen polar coordinates before in your pre-calculus course. Well, depending on how does that go, I'm not sure, but most pre-calculus courses cover just a very intro polar coordinate, which is exactly the same scope of what we're going to do in this section, because, well, we're not going to do any calculus yet. We're going to describe what it is, where it comes from, and what do we use it for. So, and well, regardless of whether you have seen it before or not, well, let's describe what it is. So far we have graphed points and equations, in the xy system, x and y. That is the rectangular system or Cartesian system. There's two ways to call this system, and and in this case, well, this is one point, simply x, y. I mean, like 3 units to the right, 5 units up, for example. So just so to speak, for one very simple example. Okay, so this is a point, an order pair x, y. However, in the polar system, we are not going to graph a rectangular motion or rectangular displacement like we do in the rectangular system. So what we're going to do in this case is plot points in terms of radius and angle. So yes, we're still going to have an origin, just like the Cartesian system. There's the origin 0, 0. And in the in the polar system, we also have an origin, but we don't call it origin. We call it the pole. And the pole is the point, the order pair that it's also 0, 0. However, it's not going to be x, y in this case. Well, we're going to go from the pole to any point in the polar plane, no longer the Cartesian plane, in the polar plane. And that point essentially is going to have a ray that goes from the origin to, or rather the pole, to that point. However, again, we're not going to displace x units, y units like in the rectangular form. So instead, our reference, which is going to be the equivalent of the x-axis, well, we're not going to call it the x-axis anymore. It's going to be called the polar axis. So I'm going to stand at the pole here, and well, the way we're going to graph these points is instead, well, displace some units. That's going to be our radius, and just like a camera, pan in a way that you create an angle between the polar axis and the ray created by the point that is away from the pole. That's going to be called theta. All right, and in this case, the order pair is going to be of the form r theta. All right. So that's how we're going to plot points this time. Not by displacing x and y, but rather by looking at some radius and some angles. Well, so what's next? What else can we describe? I think that's pretty much it about how we describe these points now. So here is the thing. Let's look at a couple of examples, and I would like to show you how the way we plot points in the polar plane, it's not unique, or the way we're going to label is not unique as opposed to the points that we plot in the Cartesian plane. For example, the point 3, 4. That's the only way that we can represent the point 3, 4, because 3, 4, there's no other way to represent it in different numbers, because otherwise changing numbers, that's a totally different point. However, In the polar plane, things are going to be a little differently. Well, so let's look at some examples so you can see what I'm talking about. So plot the points with the following polar coordinates and represent their location in at least two different ways. Well, that's what I was talking about the uniqueness of representing a point in in rectangular system versus the points in the polar system. It's not unique. All right. So let me draw the axis. And notice the way these graphs look like. We have these circles here. These circles right here pretty much represent the radii that we want to plot for the given angles. And also look at these rays that we have here, at these diagonal lines. That's going to help us represent the angles with respect to not the x-axis, but the polar axis in this case. All right. Well, so we want to plot the point 3, 60. In this case, well, I'm gonna go from the pole. I'm gonna go a radius of 3, and then I'm gonna pan my camera to 60 degrees, which is going to be here. All right. That's our 60-degree angle, and that's the ray generated by that point coming from the pole. Well, that's 360. Well, they're also asking us to represent this location in at least two different ways. Actually, I'm going to do many ways, not just two. Because, well, it's important to get used to different versions of this. Actually, well, so here is the thing. In this case, polar coordinates are related to trigonometric functions. And well, what do we know about trigonometric functions? Well, they're periodic. You know, those trigonometric functions, which are also known as circular functions, they're periodic of period 2 pi. That means that if I start here, and if I add 360 degrees, I'm going to get back to the same point. That didn't happen in the rectangular system. Like I mentioned before, the point 3, 4 is unique, and there's no other way to represent the point 3, 4. If you change the number in any of the coordinates, well, you're somewhere else. It's no longer the point 3, 4, as opposed to, in this case, polar coordinates. Well, so another way to say this is the same radius, 3, and if we add 360 degrees, is that 420 degrees? So that's the same. That takes us back to the same point. What if we add another multiple of 360 degrees? Well, that's 780 degrees. All right. That's another way to represent the same point. And again, this is due to the periodic properties of the trigonometric functions that are behind this circular points, if we will. Let's call them circular points for now, but really these are called polar points in the polar system. We will get into the trigonometry behind those points in a few minutes. All right. There is another way to represent this point. All right. If we reflect, check this out. If we reflect this point right here to over here, it turns out that it is exactly the same point, even though the location is different. However, in this case, well, what's the angle between the polar axis and the location here? In this case, this is the angle 240 degrees. However, we can modify the radius in a way that it takes us back to the point we were at. In this case, well, it's still 3 units. However, what happens if we change the sign to the number? This is changing the number to the radius is going to take us back to the original location in the first quadrant. This one is a little weird, but it's very important to get used to it because we're going to use it a lot throughout the rest of the section. We're going to use this idea a lot in the following section. And of course, you're going to use it a lot in Calculus 3 next semester when you apply a lot of this polar and cylindrical, potentially cylindrical and spherical coordinates. Well, you'll see about it. Well, we can do the same, adding 360 degrees. That's a negative 3 plus 360 degrees. That's going to be 600 degrees. All right, and add another multiple of 360 degrees. That's negative 3 comma 960 degrees. Well, is that the only way to represent this point? Well, notice I have 6 different ways to represent it now. But in this case, notice I only added positive multiples of 360 degrees. Now, can we do the same by subtracting those multiples? Yes, of course, because the periodicity of these points, it goes in either direction, in the positive direction, counterclockwise, or in the negative direction, clockwise. So instead of adding 360 degrees to get 420 degrees, we can instead subtract 360 degrees, and that's going to be 3 comma negative 300 degrees. All right, so instead I'm going to go clockwise, and that's going to take us back to negative 300 degrees. Keep subtracting another multiple of 360 degrees. Well, that's a negative 660 degrees. And so on and so forth. I mean, infinitely many multiples of 360 degrees. We don't have to do too many. All I want you guys to do is so you can see the picture of how we can represent these points not in a unique way as opposed to points in the rectangular system. All right. Let's look at another example. The next example they're giving us the angle in radian. It's the same thing. Nothing's going to change. So it's also a radius of 3. So from the pole, I'm going to move 1, 2, 3 units as a radius, and I'm going to go with an angle of 3 pi over 4. That is, here is a pi over 4, 2 pi over 4, 3 pi over 4 is here. So that's the angle 3 pi over 4. All right. Well, can we represent this this point in a different way? Of course. Again, what if we add, well, in this case, I'm not going to add 360 degrees. Well, essentially I will. However, I will add 2 pi. I mean the 360 degrees, but in the pi version, in the radian version. So that's 3, comma, add 2 pi to 3 pi over 4. You should get 11 pi over 4. Is there another way? Of course, add another multiple of 2 pi. That's 3. And 3, that's 19 pi over 4. Can we go in the opposite direction? Of course. So if we go in the opposite direction, I'm going to go back to some negative angle. And what's that negative angle? That negative angle will be negative, let's see, I believe that's a negative 5 pi over 4, right? Negative 5 pi over 4. So this is what we're doing, just adding positive multiples of 2 pi and subtracting multiples of 2 pi. Again, because that's what comprises one whole cycle, one whole round in this case, adding 2 pi. And that's something we know from trigonometry, right? And that's what makes it pretty cool about polar coordinates, the fact that we can represent these points in more than one way as opposed to just a unique way in the rectangular system. Of course, can we do the same with the negative radius? Of course, yes. Let me go in this direction. That's the point. In this case, well, That's going to be number 1. Okay, I'm going to go negative pi over 4 and 3. However, in order to take us back to the original location, we need to change the radius. That's valid. That's a valid move. Essentially what we're doing. So instead, in this case, it doesn't matter which one do you do first. You can do the radius first and then the angle. You can do the angle first and then the radius. In the same way with x, I mean, you can do the displacement in the x direction and then the displacement in the y direction, or you can do the displacement, the vertical displacement in the y direction and then the horizontal displacement, as long as you write them in the correct order x, y. Same here with the points in polar system. As long as you just write them in the correct form, that's fine. So what we're doing here is I'm going negative pi over 4, but to go back to the original location, change the sign of the radius. Right? I know it's kind of weird. It's weird to have a negative radius because, I mean, we're talking about a geometric shape, essentially a circle. How come a circle has a negative radius? That doesn't make sense because radius should be a positive distance, a distance that we can see, you know. But in this case, this sign is just it's just a tool to fix this and take us back to the original location. That's all it is. All right? Kind of weird, I know. But anyway, that's how it works. This same location, if we use this as a reference, another way to name this point, call it 7 pi over 4. And of course, you can keep adding multiples up to pi or subtracting multiples up to pi, just the same way that we did before. All right. Now, so right now, what we have done is just see how it works to plot points in the polar system. However, what if we are working on a system, say the rectangular system, and we want to know what's the equivalent point in the polar system, or vice versa? What if we have a point in the polar system and we want to know its equivalent in the what's it called, in the rectangular system? So there has to be a way to go from one world to the other and then go back to the original world. Well, of course, we have formulas for that, and the formulas for that are here in the next page, and these formulas are to convert these points between one system and the other. And well, in this case, I mean, everything comes from basic trigonometry, because if you plot a point, all right, so that's x, y, essentially r and theta. Well, this point right here essentially is going to form a right triangle. And that point, which is r units away from the pole, well, that's forming an angle with respect to the polar axis, which is the analogous of the x-axis in the rectangular system. Now, if we use trigonometry to find this y and this x, well, x over r equals to, this is adjacent over hypotenuse, that's cosine theta, which results into x equals r cosine theta, which is this formula right here. And same here, y over r equals sine theta, which results into saying y equals r sine theta, which is that second formula, where that second formula is coming from. And these two formulas are to retrieve the x and y location given a radius and an angle in this case. How do we get the other formulas to convert from Cartesian to polar? Well, so essentially, when we convert from Cartesian to polar, we form this right triangle. So we need to find a radius and an angle. Well, so the radius is really easy. Is very intuitive rather to find, because in this case, well, we're forming this right triangle, and we want to find the distance between the pole and whether in the location of the point in whatever system, and that's simply the result of using the Pythagorean theorem: c squared equals a squared plus b squared. And in this case, well, what do we have? R squared, which is our hypotenuse, and that's x squared plus y squared. Solve for r. That's simply a Pythagorean theorem problem, essentially. All right. And while the angle theta is the arctangent of y over x, well, y over x equals tangent. Solve for theta, you get the arctangent formula. So again, it's very basic trigonometric functions and Pythagorean theorem. That's where it all stems from. How about we look at some examples on how we convert between one system and the other. So they're asking us to find the rectangular coordinates of the point that contains the polar coordinate 6 comma pi over 6. It would be great if we label this as an r equals to 6 and theta equals to pi over 6. Okay? And all we're going to do is just use the formulas that we obtained using this triangle setup, where x equals r cosine theta, and y, equals r sine theta. And I think this relates with what we did in parametric equations at the beginning of the chapter when we were parameterizing circles. Remember that? How we use this generalized version to parameterize a circle. So, and again, here's where the connections start to show. The fact that we're working with polar coordinates, that's really related to these circular functions, that is, these trigonometric functions. And well, all we do is substitute the values. That's a 6 cosine pi over 6 and 6 sine pi over 6. Well, simplify, and that's root of 3 over 2 in 1/2. Cosine pi over 6 is root of 3 over 2, and sine pi over 6 is 1/2. And in this case, we'll just simplify 6 over 2. 6 over 2, that's 3 root of 3, and that's a 3. Well, these are the results of converting the corresponding r and theta into x and y. That means 6 comma pi over 6 is the same as saying 3 root of 3 comma 3. And again, worth noting, this is unique. A point in Cartesian coordinates is unique. There is a unique representation. However, this is not unique. Okay, not a unique representation. Unique representation. All right. It's very formulaic. X is the cosine, y is the sine. In the same way that you memorize your unit circle back in trigonometry, when you first learn about how to obtain the values of the trigonometric function. So you would look at these order pairs on the unit circle. The x coordinate relates the cosine function. The y coordinate represents the sine function. And I think there's another big connection with that. All right. Let's look at another example. For the next example, we are given a couple of order pairs in rectangular form, but they're asking us to convert them to polar. And in this case, well, when it comes to convert from Cartesian to polar, my advice is to first graph the point, especially because of the angle, which is usually an issue when it comes to finding the angle. So number one, okay. So this looks a lot like the following point. Well, 1 unit and square root of 3 units. So that's the point that we want to plot. And this forms this right triangle over here. All right? Well, so number one, we want to find the radius. That is, what's the distance between the pole and the point on the plane. Well, so number one, let's use the formula r squared, or rather r equals the square root of x squared plus y squared, where in this case this is our x and this is our y. Again, it's an ordered pair in Cartesian plane, x, y. Just plug in the values, simplify, whatever we get, that's going to be our radius. Well, so r equals to the square root of 1 squared plus the square root of 3 quantity squared. R equals to 1 plus cancel the root with the square, that's 3. That's the square root of 4, which is equal to 2. So we already have the radius, which is 2. We need to find the angle. All right, how do we find the angle? Well, in this case, you might want to, well, so there's a couple of ways that you can find the angle. Number one, you can use the inverse tangent function. However, look at this angle. Look at this point. Isn't it that this point is one of those special points in the unit circle? I mean, except for the division by 2, but essentially it's the same. From here, I can already see that this is an angle of 60 degrees, which is the same as saying pi over 3. All right? Unless you're giving a different value, a different angle, well, just use the arctangent function and round it to decimals. Well, that will depend on the instructions, whether in a homework, on an exam, or just leave it indicated in terms of arctangent, all right? But in many situations like this, I mean, we are getting these standard triangles or our special triangles, the 30, 60, or the 45 degree. But we need to be very, very careful which quadrant are we locating this point, all right? Okay, so let's look at the next example. 1 comma negative 1. And let's plot the point. So that's going to be the following point. That's a 1 and negative 1. So number one, let's find the radius. To find the radius, r equals the square root of x squared plus y squared. And that's the square root of 1 squared plus negative 1 squared. Those are the coordinates of the given point. And well, let's just simplify this. That's 1 plus 1, which is the square root of 2. So we already got the radius, which is the square root of 2. We need to find the angle. And again, if you want to use the arctangent function, by all means. However, I think this is another of those special triangles. 1, negative 1. In this case, well, this is a 45-degree angle, but a 45-degree angle in the fourth quadrant. However, if we use as a reference our polar axis, that's essentially 7 pi over 4. Or negative pi over 4. Recall that these angles can be represented in pretty much infinitely many ways, so you get to choose which one is it. So I'm going to go with 7 pi over 4. And I know you could argue about if you use the theta equals arctan of y over x, essentially we're working with the arctangent function, and the arctangent function has actually a restricted range that goes from not inclusive negative pi over 2 to pi over 2. All right, but in this case it's that restriction is for the arctangent function, but in this case, since we are looking at these points that can be represented in infinitely many ways, well, it's valid to use angles that are outside of the range of the arctangent function. So in this case, it's fine. All right. So that's another example. Or again, you can represent this using the negative pi over 4 or any other multiple, 2 pi multiple of the given angle. All right. So that's how we go between one system and the other system. So this is a way that we go using these formulas, which is essentially basic trigonometry and Pythagorean theorem. All right. So now let's talk about polar curves. So now we're going to get into graphing. Well, not graphing, but rather getting into the analytic geometry of this polar equation. So in the same way that we have a library of functions in rectangular system, we have parabolas, we have other curves, we have lines, we have circles, we have many shapes that are described by equations. So it turns out that we have equations that are described in the polar system. And well, in some cases they are very compact equations. In some other cases, we need to do some work before we can describe what they are. Like, for example, let's look at the first example. For letter A, what do we have in this case? R equals to 5. That's all they're telling us. However, what has come to your mind when you read this R equals to 5? Any ideas? What? Yes. It's a circle, right? Because I mean, what other shape essentially has a radius? Basically a circle, right? That's the only one that we can think. Of course, I mean, ellipses fall into that category, but that's a little more complicated. Well, we're not going to discuss that one here. But yes, for the sake of simplicity, well, r equals to 5. That's something that has a radius of equal to 5, and essentially a circle of radius 5. That's what we are picturing in our minds for now. Let's do the transformation of coordinates to verify that idea. Okay, instead of scrolling up and down, let me just write this the conversion formulas. R equals to square root of x squared plus y squared, and theta equals arctan of y over x. Also, we will need to use x equals r cosine theta and y equals r sine theta. So we're going to use this a lot. All right? Well, so what I'm going to do here is go from the world of r theta to the world of x, y. So I'm going to replace this r, this little r for radius, into something that relates x's and y's. In particular, we know this formula from Pythagorean theorem, from the conversion of formulas. So I'm going to replace with that. So I'm going to replace r with the square root of x squared plus y squared equals to 5, because let me box it so you can see where am I getting this from. And well, let's get rid of the radical by squaring both sides. That's x squared plus y squared equals to 25. All right? Is that the equation that represents a circle of radius 5? Yes, indeed. And graph. -5, -5, 5, and 5. All right? It's just conversions using these formulas, or identities, if you will. All right, the next one, letter B. That one might be a little tricky. All right. Theta equals pi over 4. What comes to your mind when you read that statement? Theta equals pi over 4.
It's an angle.
It's an angle. It's something that has that angle. What could that something be?
Still a line.
A line, right? I mean, there's no other shape for which all infinitely many points are pi over 4 radians with a reference with the polar axis. So there's no other way, all right? Well, so that's what we are expecting to get in this case. Well, so in this case, let me do the graph first. Let me do the graph, and then I'm going to do the algebra. The algebra is going to be a little tricky. So that's theta. Oh. That's going to be a little tricky with the algebra, but you'll see how's that going to work. So that's going to be the line. And let me write down the angle in this case, which is pi over 4. All right? Well, So theta equals, hmm. So here's what we're going to do. I'm going to take tangent on both sides. Tangent theta equals tangent of pi over 4. All right? So what's tangent in this case? So I'm going to fix this formula that I had over here, the one that says theta equals arctangent of yx, or y over x, and I'm going to take tangent on both sides, or essentially solve for y over x. That's gonna be tangent theta equals y over x, and I'm going to replace this tangent theta with y over x, and tangent of pi over 4. What's that? Isn't that I think it's 1? Solve for y equals x. Is that the same linear equation? The one that passes through the origin? The same thing. All right? The next one might be a little tricky as well, because what do we have over here? We have r equals to 2 cosine theta. And well, here is where we will connect the trigonometric function sines and cosine with the formulas r cosine and r sine. However, we notice in this case that we are missing something in a way that we can, relate these formulas. So we wished we had an r over here, right? We wish we had an r over here so we can actually turn this into an x, right? We can make our wish come true actually. Why not? Multiply both sides by r, turn this into an r squared, and this is 2r cosine theta. Alright, let me highlight something here. R cosine theta from our formulas that equals to x, and r squared, that's essentially the x squared plus y squared. Essentially this radical solve for the variables x squared plus y squared, right, when we square it. And well, so replacing, that's an x squared plus y squared equals to 2x. So far, that's just the equation in rectangular form, but it's kind of hard to tell. What is this graph. What's the graph of this equation? Well, by looking at the quadratic terms, both of them are positive. So that could either be an ellipse or a circle, because if one of them is negative, then we have a hyperbola. But we also have that 2x like kind of in the middle of nowhere. So we will have to do a little bit of algebra to rewrite the equation in a more convenient way so we can actually identify what it is. So I can already tell it is a circle because the coefficients or the denominators of the quadratic terms are both the same, are 1. So if we had different numbers, different coefficients or different denominators, that would be describing an ellipse in this case. That is, the largest number of on the coefficient, or rather in the denominator actually, would be related to the length of the major axis, and the smaller one, the length of the minor axis in the ellipse. But well, this is a circle, and let's write it in the way that we can actually interpret its properties, that is radius and center. We cannot tell what the radius and the center is in this form, so we can actually graph it. So what I'm going to do in this case is move all the variable terms to the left hand side, x squared minus 2x, and I'm going to leave a space over here, blank, plus y equals essentially 0, isn't it?
Yeah, but where's the x, y squared?
But because I'm adding a blank, if we add a blank on one side of the equation, add it to the other side as well. What is this blank for? See, this blank for is to find that magical mystery number that will complete the square. That is to turn this into a perfect square trinomial and then factor it as a binomial square. Well, to get that magical mystery number, essentially what we do is divide our middle coefficient, that is the number that multiplies x to the first power, divided by 2 and square. So that's going to be negative 1 squared, which is 1. So I'm going to add a 1. If I add a 1 on the left hand side, then I have to add it on the right hand side to keep it balanced. And well, what's this?
What's that supposed to be y squared? squared after plus 1 on the back.
Oh, yes, that's a y squared. Thank you. So y squared. Let me make this look like a plus sign, not like a t. Thank you. So, well, when we add this magical mystery number, that's guaranteed to be a perfect square trinomial, which can be factored as a binomial square. That is, the square root of the first term, which is x, the sine of the middle term, and the square root of the third term squared plus y squared equals to 1. So this is an equation of a circle. Now, if you want a better visual of this, you can interpret this equation the following way: y minus 0, if you will. So we can easily see the HK point for corresponding to the center. So that's the process to complete the square. We always divide the middle coefficient by 2 and then square so we can get a perfect square trinomial. Let me give you another example. For example, when we have x squared plus, let me do 8x plus blank. What number will turn this into a perfect square trinomial? Well, divide 8 by 2, that's going to be a 4. And then squared, that's a 16. And then we can factor this as x plus 4 squared. Expand the binomial, you should get back to this. All right? And well, let's graph this circle. And essentially, this circle has a radius equal to 1 and a center at the point 1, 0. Well, so let me go to the point 1, 0 and displace 1 unit in each direction to plot this graph of the circle. All right? And that's how we describe this circle. Notice it's not a notice that despite this being a circle, it took us a little more work than the circle that we got in part A, because for the circle in part A is like the simplest case of a circle. That is the circle that is centered at the origin. When it's shifted either horizontally or vertically, well, that's where we have some issues with it. You know, we have to do a little more of work. All right.